lastly, before we stick numbers in, yeah, I have mu s times this whole thing here, so just divide by that. And I end up with mu s equals v squared cosine theta minus gr sine theta over gr cosine theta plus v squared sine theta. And now plug and chug. So it's 30 squared cosine of 25 degrees minus 9.8 times 100 times the sine of 25 degrees divided by 9.8 times 100 times the cosine of 25 degrees plus 30 squared sine of theta. And we get like stone, they're relying on you.
.3165.
Trust that that is correct. All right, so what are the units?
No units.
Correct. All right, questions?
Is this going to be a question on the test?
I've asked questions like this on previous tests.
It's going to be as long as this one.
Well, yeah, pretty much. The last time I put this on a test, I said, give me the equations in terms of, and I told you what letters to have in the end. You didn't actually have to solve it, you just had to get, I think it was this far.
Oh, no.
And there are other variations of the same thing. All right, all this is well and good, but are there any other types of circuit? We did the thing attached to the rope. We did the car going around a banked curve. And again, banked curve means it's at an angle as you drive around it like this. And are there other circular motion problems that we should address? And of course, the answer is yes. We now get into space. So let's start out with Earth. Satellite. So why would a satellite orbit Earth?
It's going fast enough to resist the pull. gravity.
What do you mean resist the pull of gravity?
Well, I guess it's falling at a speed that as it falls, it's going around the Earth.
Okay. Now, I think it was Newton who came up with a thought experiment of if I take the Earth with a mountain and I stick a cannon on top of the mountain. If I shoot the cannon, ball's gonna go. As I shoot it faster, it'll go farther. As even faster, it'll go farther. There is a speed at which if I shoot it, it will keep falling towards the Earth, but just keep missing the Earth, as Logan was laying out. Once it gets to that speed, then we're dealing with orbit. So Newton speculates that all things that are orbiting the Earth are doing so because it's constantly falling, but just keeps missing, which was I want to say Phantom Tollbooth was the children's book, in which that's how somebody flew, by throwing themselves at the ground. No, throwing themselves at the ground and missing. I think it's Phantom Tollbooth. Hitchhiker's Guide is you throw yourself at the Earth and get distracted. So since the satellite is not moving in a straight line, what must be true? All objects maintain a velocity unless something happens. What is that something?
Encounters another force.
Yeah. And what is the force in this case? If this thing's going around the Earth, what is the force? It is a centripetal force, but that's not the name of the force. That just happens to be what it is. Or badly worded. It will be a centripetal force, but that's not what it's not part of FTOM.
Weight.
It's not really considered weight at this point, but
Gravity. Now is the gravity that's on it, because it's a big object.
it is big object, little object. Little object's not close enough to the surface of the Earth to make it be called weight. Gravity is not the name of the force. What is the name of the force?
Acceleration.
Acceleration is not a force. It is so simple that you're overlooking it. Okay, gravity, huge topic, of which we're looking at tiny little bits of it.
That's a big old thing, though. Earth is pretty big.
Compared to a satellite, yeah. I'll agree with that.
Well, does it start with?
Either G or F, depending on how you want to word it. Interesting.
Gravitational force.
Pardon?
Gravitation.
Yeah, that works. Or force due to gravity, either one. All right, so we have some sort of gravitational force pulling on it. It's pulling towards the Earth, and it's also pulling the Earth towards it. Forces come in pairs. I can't really get away with W anymore, so F sub G for the gravitational force. So all we have to do is figure out what is the gravitational force. Now, mg would work really nicely if I know what the acceleration due to gravity is that far out in space. I mean, if it's 100 kilometers from the surface of the Earth, what's the acceleration due to gravity? It's not 9.8. So we need a formula here. If I'm dealing with gravitational pull, upon what do you think it would depend? What would affect the force due to gravity here?
The mass of the larger object and its distance from the smaller object.
All right, one more thing. There'd be two more letters I'm gonna throw into here, but,
Is V one of them?
pardon?
V? Is that what?
V, no.
Okay,
So how fast it's going doesn't affect the actual force. At least not in classical mechanics.
G.
Which G?
Little G.
Big
Big
G.
G.
It is big G. That is known as the gravitational constant. The third thing that students will call gravity. Gravitational constant. If you look back in older textbooks, they'll call it the universal gravitational constant. But it's not really called that anymore because we really don't know if that value is the same everywhere in the universe. But occasionally, I call it the universal gravitational constant. Not a bad habit. We're still missing something. All right, from a math point of view, I know that the force that they exert on each other is the same magnitude. Newton's third law. So, if I look at it from the satellite's point of view, or from the Earth's point of view, that gravitational force should be the same. So, it has something to do, it has to have something to do with both masses. Also, when I flip the masses, I should still get the same magnitude of force. In other words, the commutative property should hold. Well, what two math operations do we have where the commutative property holds? In other words, where the order does not matter, which you do it. Yeah. So mathematically, it's got to be one of those two, and it's multiplication. Now, over R squared, I'm just presenting that to you. There are groups that try to figure out, is it really R squared? Maybe it's R to the 2.0001 or something like that. And if you looked up how close they've gotten to, is it 2, they just say the difference between the actual number and 2 is less than 0.00000001. So they definitely have not shown that it's something other than 2, but it's darn close to 2 if it's not exactly 2. Now the 2 actually makes some sense, because imagine, there's some vector stuff missing here. We'll bring that in just a moment. So imagine that Earth, well, actually, let's do it this way. I have a universe here, in which there is the Earth. Into this, so this is the only thing. I am playing God, created the universe, I put a planet into it. Now, I put a satellite in motion. It's going to be pulled towards the Earth, so which will put it into centripetal motion. How does the satellite know that the Earth exists in order to orbit?
There's a gravitational force that it is within range of, and it got stuck in it.
A gravitational force.
Around the Earth, there is a circle or a shape of some sort that has a gravitational force that is pulling the satellite in, and once the satellite gets into it, it knows that it's there.
All right, changing one word instead of force and field.
Okay.
Because gravitational force depends on both masses, but in order for that gravitational force to exist, each mass needs to be aware of the other one. It's not suddenly disappears and it goes, ooh, now there's 2 of us. How does it know the second one exists? So it's giving off something, which we, for lack of a better term, call a gravitational field. So imagine Earth is giving off this signal, this field. Sort of like to think of it as gravitational pheromones, but no one else will understand that reference except for potentially previous students. It gives off this something. It sends these signals out, which the satellite's going to notice. If it sends out a pulse of gravitons, of this, whatever this is, well, it sends off this pulse. That pulse is going to start really close to the size of the Earth, and then it's going to expand. Well, as it expands, the area over which this whole thing is spread is very much related to the surface area. And what is the surface area of a sphere? The formula for the surface area of a sphere. Pardon me?
You said the volume formula?
No, surface area formula. And I assume Dominic's looking it up. Somebody beat Dominic to it.
4 pi r squared.
Yeah. There's that r squared. So whatever these when these gravitons are released and they're moving out, that they get spread over whatever r squared is. So the farther you are away, the more it gets spread out, the fewer gravitons are going to hit the satellite. And so justification for the r squared term. Now, big G, this gravitational constant depends upon the units you're using. If we're talking about SI system, so mass would be in kilograms, R would be in meters, F is in newtons, G is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared.
Isn't that just a formula that we're?
That's just a number. It would be on a quiz or test, it'd be at the top of the first page. Or quiz, I guess, top of the page. But it also gives you some idea why we've ignored this, because I talked early on when we was first introducing FTOM, that for there to be a gravitational force, you just need two masses. Well, the mass between me and Brian, and I'm going to make up your mass, figured out about 100 kilograms. Brian, I'm just going to go with 70 kilograms because that's average US adult. Times 6.67 times 10 to the negative 11th, divided by 4 meters, over 4 meters squared. We end up with something tiny. Let's see, this is roughly 450 times 100, so 45,000 over 16, so I'm getting around somewhere around 4.5, 4 times 10 to the negative 11th divided by 16, so that's even smaller. So we're talking something on the order of 10 to the negative 12th newtons. It is so tiny that unless you're conducting gravitation experiments, you will not notice it. So, let's do a little centripetal motion problem here. I have Earth, Earth 1. I have a satellite. And let's figure out, let's say that we have this is the Earth radius of the Earth, and this will be at basically a height of the equivalent of the radius of the Earth. So we end up with, well, we've already done the fourth diagram over there. So we have F sub G is equal to MA sub C. This is mass of a satellite. We don't need to break anything up because the direction of acceleration is towards the center of the circle. Substitution, well, we now have another formula that's independent of the problem, and this is big G, mass of satellite, mass of Earth, over R squared is equal to mass of satellite times V squared over R. So in my equation here, I have little r. What is little r in terms of our problem?
The radius of an arc.
Is it the 2 times the other r?
2 times big R. Yes. It's the center to center distance. Now, quick evidence, assuming that formula is correct, quick evidence that it can't be the surface. The surface distance is, if you went outside and touched the ground, if it were surface to surface distance, this R would be close to 0, which means that force would be incredibly huge. And we can easily break away from that. So it's center to center distance, as long as you're outside of the Earth. So this R is from here to here. This is little r, center to center. Mass of the satellite is irrelevant. So we're left with big G, mass of Earth. See, that R's canceling out with one of those over R is equal to V squared, just V squared. Well, I have something traveling in a circle. So what's V? What's the formula for speed of something traveling in a circle? This is one of the first things I wrote today.
So distance over time.
Okay, and what's the distance?
Circumference.
Yes. So this is 2 pi r squared over the time. Good. Went too far there. Well, let's do this. 2 pi r over t, big T